Welcome back, ladies and gentlemen. So, we have started our path at looking at things going at constant velocity. And after we've kind of looked at one object going in a rather, not complicated, but a more complicated setup than just something going one way, we're going to now start talking about and practicing a little bit what happens if I have two objects that are moving and how we can kind of read a position time graph to figure out what's going on. All right? Now, our first worksheet was very much me kind of leading us through how to do the first half and then kind of letting you work at your own pace in the second part. And I know this is kind of virtual, so it makes it a little bit more at your own pace sort of thing. But for this particular worksheet, this is going to be a very focused on you doing it. So going through, giving your best guess, and I'm going to review the different questions. All right? But this is not going to be a worksheet where I kind of go through and kind of go step by step exactly what's happening. Instead, I'm going to talk about the answers. This is going to happen from time to time throughout the year. We'll have certain worksheets that are going to be very much, I'm discussing what's going on. We do some practice. We do kind of some practice where I'm guiding us and we're going through it. And then there's going to be some ones where you're doing most of the work. All right? So if you are working on this at home, it would be really useful, and you don't have to do this, but if you can kind of maybe, Zoom, Google Hangout, FaceTime with someone who's also in this class and kind of work on it together if you want. That might be a really useful way to kind of practice, because generally in class, that's how we do things. We do group work. This can be kind of difficult for at least the first semester. Hopefully the second semester will be a little easier. But with that being said, I've talked too much. For worksheet number 2, we have a position time graph. And this time we have the position time graph of two different cyclists. All right, so cyclist A and cyclist B. Now, they both start in different positions, as you can kind of see on the graph, at time equals 0. And basically, I want you to use that graph up there to answer some of the questions. All right, so as you can kind of see from this, part A, the first question is, do the cyclists start at the same point? How do you know? If not, which is ahead? I've already kind of given you a hint if you were listening, what the first part of the answer might be. So what I want you to do, please, is I want you basically to pause the video here, and I want you to work through all of question 3. All right, so I think there's 5 or 6 parts, A through E. Work through them to the best of your ability. Once you think you're ready, unpause the video, and we'll talk about the answers. All right? All right, so hopefully you have had a chance, ladies and gentlemen, to work through part or question 3 and all the different parts for it. So let's review. So to start with, do the cyclists start at the same point? How do you know? If not, which is ahead? I am going to minimize real quick so we can see the full answer. Okay, so right away we can say the cyclists do not start at the same point. And if we look at that graph, remember, position time graph, the vertical axis tells me where I am. The horizontal axis tells me at what time I'm at that position. Okay? And we want to get this, we want to kind of get this through, kind of think about it, the idea that it isn't just an X and a Y axis anymore. The axes of this graph physically represent something. Okay? And we're going to bring that up throughout the year. We're going to keep looking at different graphs. They mean different things in the physical world. They don't just mean an X and a Y. Okay? So, they do not start at the same position. We can look and see they do not have the same starting position t equals 0. If we look at the graph, it looks like cyclist A does start at the origin, a position of 0 meters. Cyclist B starts in front, so a position that is farther forward. And you see my answer, I say that's higher than 0. I don't like that. I don't like saying higher because it makes you think that it's like on top of it. So instead, I want you to say cyclist B starts at a position that is in front of cyclist A, all right, or farther forward than x equals 0 meters. So when it all comes down, cyclist B is ahead of cyclist A when they start. All right, right there. Just, you can also at any point in time, if you think I talk too fast, just pause it. You can literally write down the answer. Okay. So that's for part A. For part B, at t equals 7 seconds, which cyclist is ahead and how do you know? So this doesn't explicitly say anything about 7 seconds, but it does tell us that something happens at 5 seconds that's rather important. All right, we're actually going to come back to that in a second. But looking at the graph, 7 seconds is going to be farther past 5 seconds. So let's say, it's right here. But if we just kind of look at 7 seconds, you'll notice now that cyclist A is now at a farther position ahead of cyclist B. So, because of that, at 7 seconds, cyclist A is now ahead. And we know this because, well, you can read that. We're going to talk about it at the end as well. But basically, we're going to find out that at t equals 5 seconds, the cyclists are at the same point. And then after it, cyclist A now moves ahead of cyclist B. Okay? Once again, we're just using what we know about reading these graphs, and I know this is all relatively new to us, but we're just getting comfortable with this idea, ladies and gentlemen, that these little graphs can tell us a ton of things about the motion of an object. So, part C, which cyclist is traveling faster at 3 seconds, and how do you know? All right, in all fairness, it really doesn't matter what time we're looking at here, because in all the points, we got to go back to what we know about velocity and speed. Okay, when we have a position versus time graph to find the velocity and speed, what do we have to do? Congratulations, if you said slope to your computer screen, not only are you right, all right, but you're also saying out into the world, into the void, that you understand physics and you're letting people know that it is the slope. So we look at the slope of these two lines. Remember, slope, if coming out of algebra 2, algebra 3, or calc, whatever math you're in, slope is just going to be the rise over the run. Another way is basically how many blocks do I go up versus how many do I go over. The steepness of the line, all these things represent the slope. In this case, if we look at the two lines, cyclist A's line is much steeper than cyclist B, so cyclist A has a much higher speed, a higher velocity than cyclist B. All right? Are their velocities equal at any time? Kind of bouncing off of that, they're not, because if they were equal, they'd have the same slope. And at no point in time do these two lines have the same slope. Now, it's interesting because at 5 seconds, something happens and they're kind of overlapping. How come that doesn't mean they have the same speed? Well, that answers part E. What's happening at the intersection of lines A and B? All right, hopefully when you saw those two graphs and you kind of thought about it for a sec, it told you that at that point in time, not only are A and B at the same time, moving for the same amount of time, they're also at the same position. So at this point, A and B are passing each other. You can basically say that A is passing B. So this is where the cyclists will meet each other at the same position. All right. So once again, if you have two lines, they still follow the exact same rules we already talked about with if there's just one line that's doing something kind of crazy. We still look for what causes it to be constant velocity. We still look for what causes it, how fast it's going, where it is, how much time it takes. All right. But once again, we're just getting used to this idea, ladies and gentlemen, that if I have a nice line on a position versus time graph, it's going to represent it's moving at a constant velocity. All right? So, same deal. You did A through E on the first part. Same deal. I want you to do A through E for question part 4 as well. All right? So now, we have a new position versus time graph. So this is what the original one looked like. This is the new one. All right, so you notice and just to make it very clear, cyclist B has not changed at all. Cyclist A is the only one that's changed something. Okay, so if you could, once again, pause the video. I want you to take as much time as you need. If you can, work with someone else. And I want you to answer A through E, and then once you're ready, unpause the video, and we'll answer those questions. All right? All right, hopefully you had some time, tripping over words here, to work through these particular questions for this new graph. All right, so let's talk about what exactly is going on here and what is different, what's the same. So for part A, how does the motion of cyclist A in the new graph compare to that of A in the previous graph? So basically, this is a fancy way of asking, what's different about cyclist A now? Okay, and to do that, we just kind of can write, maybe if we weren't quite sure where to start, just write down some observations about the motion of cyclist A in the beginning, before and after this new graph. So in the first graph, cyclist A is moving with a constant velocity, which is no different than this one. It's also moving at a constant velocity. All right. But in the first graph, cyclist A starts at the origin. In the second graph, we can clearly see that cyclist A starts in front of the origin at some positive position. So right away, that's one difference we can say. We can say they have a different starting position. The other thing we can notice is that cyclist A is moving with a constant velocity in the positive direction. You'll notice because it has a positive slope. I'm going to start calling it a constant positive velocity. So if you start hearing me say something like that, I'm incorporating the direction as well. So there's a constant positive velocity. Cyclist A in the new graph, however, is now moving with a constant velocity, but in the negative direction. So this is going to be the other difference. So the two differences, the starting position is different for cyclist A in the new graph, and cyclist A is now moving with a constant negative velocity in the new graph. All right, and that's what we can see in this answer right here. Covers both of them. So for part B, how does the motion of cyclist B in the new graph compare of that of B in the previous graph? I kind of said it, just kind of setting the stage, but the B line is exactly the same in both cases. So the motion of cyclist B does not change at all. Okay, has the same starting position, has the same slope, has the same everything. And I know it might look slightly different. More than likely in this class, I'm not going to try and trick you by making things that look almost the same. So if they look the same, you can assume they're going to be the same. All right? So part C, which cyclist has the greater speed and how do you know? All right? So speed, remember, once again, we find speed by looking for that slope. Speed only cares about how fast you're going. So speed only cares about the number. It doesn't care about the direction. All right? So if we look at that, if we're looking at these two things, cyclist A is the steeper of the two lines. All right? Now, one thing you're going to write down is you might look at this line and say, yeah, but it has a negative speed. It has a negative velocity. That means it has to be less because this is a positive velocity. All right? And once again, I want to make it clear, in physics, positive and negative do not mean bigger or smaller. They mean you're either going in the positive direction or the negative direction. Okay? So because of that, even though A is going in the negative direction, its slope is steeper, so cyclist A is going to have a higher speed than cyclist B. All right? And then once again, describe what is happening at the intersection of lines A and B. The rules haven't changed at all. It just means that at that particular point in time, they're at the same position, so A and B are passing each other once again. In the first graph, the original one, A and B, when they were passing, A was going in front of B. But in the new graph, you have A and B going in opposite directions. So they're basically just kind of passing each other, and then they keep going on their merry way, which leads nicely to part E. All right? Now, this one's going to be, I have to think a little bit more, but I'm confident in y'all, you know what you're doing. Which cyclist has traveled at a greater distance during the first 5 seconds, and how do you know? All right? Now, distance is just basically, remember, how far something travels. So it's basically just kind of how far, the distance-wise, how far it's gone in general. And I think I just used distance to define distance, so that's really, very useful. But basically, it's just how far it travels. All right? And if you've watched the video that talks about kind of our definitions for the different things we run into in constant velocity, all right, we'll understand what distance is. So if we look at it, the first 5 seconds, we're looking at cyclist A and cyclist B. Cyclist A starts, I don't know, some position ahead of the origin. It starts moving towards the origin. But you'll notice that it's moved its position has changed more in those 5 seconds than cyclist B's position has. All right? Just to make it a little clear, I can draw a little line. That's how it looks like how far cyclist A is gone. That would be how far cyclist B is gone. Because the thing about these graphs is that really what they're doing is basically the position axis is the equivalent of what it looks like. It would be like if the little bike is going to be the world's greatest bike. Don't worry. All right? It basically is showing what happens if I look at the bike going across this. All right? And of course, if I just made this even more confusing, just erase it. Don't worry about it. But with that being said, of the two, cyclist A has traveled a farther distance than cyclist B has in that time. And if we think about it and connect it back to speed and velocity, that makes sense because cyclist A is moving faster than cyclist B. And if they move for the same amount of time, that means that I must have gone a farther distance. All right? It's the same idea if I have two people on the interstate. One's going 60 miles an hour. One's going 50 miles an hour. Well, in 10 minutes, the person going 60 miles an hour has gone a farther distance than the one that's going slower. Okay? So, right there, ladies and gentlemen, that's kind of our first real practice where you guys are kind of working, with group members, working with yourself, using what we've talked about in the previous kind of guided practice. All right? Once again, if you have any questions, shoot me an email, come to office hours, or talk to me in class. All right? But with that being said, ladies and gentlemen, that's kind of where we're going to stop for this particular review. So, have a great rest of the day, and I'll talk to you later.